Just like with weak acids, we have a generic formula for the dissociation of weak bases. And in this case, a weak base is represented simply with a B. When it reacts with water, remember it's a proton acceptor, so it becomes HB with a positive charge, or one more than it originally had, plus hydroxide, because hydroxide lost its proton to the base. Now, again, just like with weak acids, we can write the equilibrium expression. In this case, it's going to be your BH or HB plus, so your conjugate acid times the concentration of hydroxide all over the concentration of your base. Remember again that water, since it's a pure substance, we don't include it in your equilibrium expression. And again, your Kb is now your base dissociation constant rather than your acid dissociation constant. Now, there are two different types of weak bases that we'll encounter in this class. The first one are neutral substances that have an atom with a non-bonding pair of electrons. And the reason why these are bases is because they can actually serve as a proton acceptor. So here are a number of different examples. The most common one that you'll see is ammonia. So you can see the lone pair of electrons, the non-bonding pair of electrons. You also have other compounds that you can see in this table, and these are amines. It's a type of organic class of molecules. The second type of weak base are simply the conjugate bases of weak acids. So for example, the fluoride ion, which is the conjugate base of hydrofluoric acid, that is a weak base. So in this reaction, I have ammonia reacting as a base. Therefore, in this reaction, I have ammonia as my weak base reacting with water, which is going to serve as my acid in this problem. Remember, double arrows because it's a weak base. Ammonia is going to accept the proton that water gives it, so it becomes NH4 with a +1 charge, and water loses its proton, so it becomes hydroxide. Now this problem is now going to be identical to the weak acid problems we previously performed. So I got to write out my ice chart. I have a concentration of 0.15 molar NH3. Remember, since this is a pure liquid, I'm actually not going to be looking at water at all, so I can just ignore that. I start with no ammonium and no hydroxide. I do know that the change is going to be minus X for ammonia, so the equilibrium concentration is going to be 0.15 minus X. I know that this is going to be plus X, and this is going to be plus X here. And so my equilibrium expression is going to be X times X, which is X squared, all over 0.15 minus X, and I'm going to set that equal to my Kb, which in this case is 1.8 times 10 to the negative fifth. I'm going to assume that my X is small enough that it won't affect my equilibrium concentration of NH3, so I'm going to ignore it to make my life easier. So X squared equals, when I multiply 0.15 by 1.8 times 10 to the negative fifth, I get 2.7 times 10 to the negative sixth. Okay, and then I need to find the square root of that, so my X is going to end up being 1.6 times 10 to the negative third molar. And so this is actually going to be my concentration. My X is my concentration of my hydroxide ions. And so what I can actually do is I can take that and plug it into my formula for POH. I'm going to find the negative log of the 1.6 times 10 to the negative third. Okay, and when I do that, I find that my POH equals 2.8. Now, I'm actually not interested in POH. I want to find my pH. So 14 minus that value gives me a pH of 11.2. And that is my final answer. So this problem is simply just a different way of applying the concepts that we've learned so far. What it tells me is that I'm going to be dissolving sodium hypochlorite into water. And so in this case, remember from previous lessons that salts actually can act as acids or bases when they're dissolved in water. And so in this case, you have ClO minus, because the sodium breaks apart because it's soluble. And so that's actually going to act as a base. It reacts with water, and I know it's going to form a base because it has no hydrogen to lose. So it's going to react with water to produce HClO and hydroxide. Okay, so we've got a weak base problem. Now I'm just going to plug in all the values that are given to me in this problem. So ICE, make my ice chart. It says the solution is made by adding sodium hypochlorite to water to make a 2-liter solution. If the pH is 10.5, how many moles of sodium hypochlorite are added to the water? Well, here's the issue. Remember, I don't need to consider water. However, all the problems so far, I've actually known what my concentration of my weak base, weak acid, strong base is. And in this problem, I actually don't. So that's going to be my X, which means I've got to figure out what the change is, because I know it's going to be plus whatever value, or sorry, minus whatever value that is, plus whatever value, plus whatever value. Well, I know I start with 0 of this, so I've got to figure out what the final concentration of these two products are in order to determine how much these values are going to change. Well, I can actually do that because I know what my pH is. My pH in this problem is 10.50, which tells me that my pOH equals 3.50, and from that I can calculate my concentration of hydroxide. So my concentration of hydroxide, all I need to do is take 10 raised to the negative this value to find my concentration of hydroxide, and I find that it's 3.16 times 10 to the negative 4th. Okay, same thing here, 3.16 times 10 to the negative 4th, which tells me that that was this value plus 3.16 times 10 to the negative 4th. Okay, which tells me this is going to be X minus that value, which is 3.16 times 10 to the negative 4th. So I've got to write this out here. The equilibrium concentration of that is going to be X minus 3.16 times 10 to the negative 4th. And the other thing that I know is my Kb. So I'm going to write my equilibrium expression here. My Kb equals the concentration of HClO times the concentration of OH all over the concentration of my weak base, which is ClO. So now I'm going to plug in the values I know. Well, I know my Kb, it's 3.33 times 10 to the negative 7th. I know the value of both of these concentrations, so I'm just going to square that value to make my life easier. So 3.16 times 10 to the negative 4th squared all over the concentration of your weak base. And now it's just a matter of solving, plugging and chugging. So I know that this is going to be 3.33 times 10 to the negative 7th times X minus, when I multiply these two together, I get 1.052 times 10 to the negative 10th. That equals 9.9856 times 10 to the negative 8th. which gives me 3.33. I'm going to take this. I'm going to add 1.05 to both sides, and I get 9.996 times 10 to the negative 8th. And then I'm going to divide both sides by the 3.33 times 10 to the negative 7th. And I find that X equals 0.300 molar. So that's the concentration. Now, for most problems, you would assume that you're done. However, there are a couple more steps here. Equilibrium concentration of sodium hypochlorite. Instead, what it's asking is how many moles are added. So if I know that the concentration is 0.300 molar, and I know the volume to which it's added, which is 2 liters, I can solve for X. And so what I will get is 0.6 moles of sodium hypochlorite. And that's it.